Don't talk about the designs on your hands. Talk about R equals theta. Why does it look like that? Here we go. Think about it the wrong way. We are used to X's and Y's, and now we are talking about R's and thetas. We're transition R's and thetas. We are used to Y equals X's. Y equals 3 plus 3 sine X. The graphs we have are R equals theta and R equals 3 plus 3 sine theta that we're going to look at. Okay? Now, what do you notice? Theta is replacing X. R is replacing Y. This is the first thing that makes polar graphs confusing. We are used to X being our input, Y being our output, independent, dependent variable. But for the polar graph that we are about to jump into, opposite. The theta is our input. We will plug angles in and we will get R's out. Why don't they put theta first then? I told you. Why do they put R then theta? Alphabetical order. That's literally the only reason why. We don't know of any other reason. We would like that to be inputs, outputs. So here's how we graph a very basic understanding. If you look at your homework, we're on a rectangular coordinate system. We don't want you to be perfect. But we ask you to graph R equals theta. Here's what you can do. And here's how you do it. You could like copy this down on your homework. I'm going to show you on your notes. You think about your inputs, your angles first. You think about your angles first. You will locate your first angle, theta equals 0. Great. I'm standing behind you two. Separate. I can't handle you two. I can't handle you two. It's like every single day. Go. Sit somewhere. Oh, I'm so shocked. I'm so shocked. So shocked. I know. You don't do anything, ever. You guys never do anything, ever. And you know what? Let's create a table of values, like theta, R theta. Here, I have theta 0, R 0. We will then add angles until we get pi. I don't know, what angles do we want to use? It's up to you. I like to use angles like pi over 3 because I know pi over 3 is close to 1, the number 1. We like to use pi over 2. Pi over 2 is very close to 3 halves or 1 1/2. 2 pi over 3, 2 pi over 3. It's not the best one to kind of do, but I don't want you to copy this down. More understand what is happening here. Like if you guys just copy down, you're not learning anything. Angle of 0, radius of 0. Angle of pi over 3, a radius of like 1. Angle of pi over 2, a radius of 1 1/2. About. Angle of 2 pi over 3, radius of 2. Angle of pi, radius of pi. We can see as our angle increases, our radius is increasing. On your homework, I wouldn't want you to be perfect. Rather, probably make sure you go through 3, 3, and make sure you go to 5, 6.28, and make sure you kind of spiral outward. Be like, yeah, it has to look like that. Now, the key is to think about your angle. And the graph isn't just created. We got to give you angles. For example, what if I asked you to sketch the graph of r equals 3, but from pi over 4 to 5 pi over 6 as your angle? You guys were all good at the beginning of class saying r equals 3 is going to look like a circle radius 3. But what if I asked you, graph r equals 3 from pi over 4 to 5 pi over 6? What would that look like? Go ahead. Show your neighbors. You have to shift your mindset from x's and y's to angles and radii. Go ahead. You can do it. Do I have to separate you two so that you pay attention? All right. So you're gonna pay attention now because like I'm all about separating bros now. Don't distract yourself. Maybe if you're away from them, you won't distract yourself. I'm separating the bros in this class from now on. Nice, Jolly. Pi over 4 is where we're going to start our graph. It's not just a circle. It's got to start and end somewhere. We could start it at 0 and trace around the radius of 3 until 2 pi, but I'm starting at pi over 4 here. I have to add angles by going counterclockwise. I will get to the angle of 5 pi over 6. You guys are good at just thinking about r equals 3 must be a circle, but getting to know why it's starting here and going counterclockwise around, that's important. That's the important stuff. So we just get this arc of the circle. Cool? That's important. Now let's go to your homework to the second question. I'm going to change it up. I don't want you to start at 0. That's a little bit too crazy. Rather, I want you to start at pi over 3. What would this look like? Well, here's what you might have to do. And if you want to, you could do it on the side. Think about what happens if you plug in pi over 3 for theta. It's pi over theta. Pi divided by pi over 3. Tell your neighbors, what's pi divided by pi over 3? Just 3. Your start of your graph should be pi over 3, 3. Now, where's 3? I don't know, approximately here. This is the start of the graph because I just changed it up on you. But now it's your job to plug in other angles. I'm not telling you what angles to plug in for this first page. On the next page, we'll be a little bit more specific about, you should probably plug in these angles. But for this page, you can maybe think about plugging in pi over 2. Maybe you want to plug in one angle between pi over 2 and pi. You're definitely going to plug in pi. What do you get? You're going to plug in 3 pi over 2. What do you get? Give it a shot. Give it a shot. All right. No. Let's see if somebody can get it. Do you have your homework, Barry? Because we're kind of working through the homework and back. So, I'm helping you out here. Wait. No. We're starting at pi over 3. Here's me plugging in pi over 3 and getting a radius of 3. That's a radius of 3. Keep going, guys. What happens when you plug in 2 pi? It's a half. Come on, we can do it. Go ahead, try it. Nice. Nice. See, here's your problem, guys. Many of you are still in X and Y land. Get out of it. Be in angle land. Everybody, plug in pi over 2. The angle pi over 2. What do you get? Plot that point. Everybody plot the point when you plug in the angle of pi over 2. Oh, nice job. Nice job. Pi over 2, plugged in, gives us 2. We could do more angles, but let's just plug in pi. Plug in pi. What happens when you plug in pi? You get a radius of 1. Now, here's where it's important, guys. The angle pi, the radius of 1. Don't go over here. At the angle pi, my radius is 1. Yeah, you see that -1 and it freaks you out? Doesn't matter. You think about things with r's and thetas. This is the point pi comma 1, or 1 comma pi. Plug in 3 pi over 2. What do you get? Pi over 3 pi over 2. Well, that's the same as pi times 2 over 3 pi. The pi's cancel. What do you get? 2/3. What happens if you plug in 2 pi? 1/2. What we end up getting is an inward spiral. And this creates a great opportunity for us to go down to the depths of Desmos. We will see Desmos' inner workings and its inner soul by looking at the graph of r equals pi over theta. We will start at pi over 3. I will go till A. I don't want you to see it yet. I'll start at pi over 3. What's flatter? I will start at pi over 3. I will go till 100,000. That's 1,000. 10,000. Here we go. And here we go. I have to see, where is it? Where is it? Where is it? Where is it? There it is. I gotta go. I gotta change my step. It jumps too fast. There you go. And it will continue to spiral inward, 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 inward. I gotta zoom in. And it'll continue to spiral inward, 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 inward. I got to keep going. Zoom in, zoom in, zoom in, zoom in. Keep going. Zoom in, zoom in, zoom in, zoom in, zoom in. Yo, we're at like 0.01. It's like, it'll keep going forever and ever and ever. As you keep plugging in bigger and bigger angles, your radius will get smaller and smaller and smaller. It's going to approach 0, but it'll never get there. You shouldn't see a hole. It should be like it's zoomed in. Anyways, I'm going to break Desmos if I do this, so let's turn this off. I can't even turn it off. Force quit! Desmos, no! Can't get the task manager. I'm literally breaking the computer. All right, well, let's hopefully it'll quit. All right. This is the idea. What about one more interesting one before we move on to what some people think are easier? Theta equals pi over 3. What does theta equal pi over 3? What do you think that looks like? In this situation, r is always 4. Or sorry, r was always 3. And it didn't matter what my theta was, provided my theta was between pi over 4 and 5 pi over 6. This one, my theta is always pi over 3. I don't care what my r is. What's this look like? Tell your neighbors, what's that look like? If your angle is always pi over 3 and your r can be anything. Must be a line that looks like this, right? Where we're going towards pi over 3, right? Oh, very good. It could have negative radius. Now, we will be thinking about negative radii land more next class. But before we get there, we need to understand positive radii land, positive polar graphs. And instead of sketching this and kind of doing the best we can like we did on the first page of our notes, I'm going to make it a little bit easier on you by looking at the second page of your homework. Because I'm going to provide a polar coordinate system. You guys remember when you played Battleship? You can't help yourself, can you? Slide up, stop. Remember when we played Battleship? I would give you angles and concentric circles so you can see the radii. Cool? This is going to help so we're not just guesstimating what a radius is at a certain location. We can be a little bit more exact. And I'm going to ask you to graph 3 plus 2 cos theta. Very similar to the first one in your notes. We're going to start with that. And you know what? Make it, no, 3 plus 2 cos theta is good. To help us graph 3 plus 2 cos theta, let's do a little experiment. Remember unit 7? Remember graphing y equals 3 plus 2 cos x? Remember graphing it in the rectangular box where you're graphing a period and you had like your vertical shifts and all your amplitude adjustments, your vertical dilations, your horizontal shifts. Could you do that for me? Can you show me that you remember how to do that? Can I feel better about myself because you can do that? Ah, it's not the B. So what you got to remember is you got A, sine or cosine, B, x plus C plus D. D is a vertical translation, which affects the midline. A is the vertical dilation, which affects the amplitude. B is a horizontal dilation, that affects the period. C is a horizontal translation. When it's inside, it affects the x's. Outside, it affects the y's. This 3, vertical translation. This 2, vertical dilation by a factor of 2. This 3 is the new midline. It shifts the graph center of 0 up to 3. This 2 adjusts the maximum in the middle, the minimum. It stretches things out. So I go to 5 and 1. This graph has a period of 2 pi. It'll start repeating at 2 pi. You want to step it out, divide that into 4 pieces. And you get pi over 2. And you got pi over 2, 3 pi over 2, 2 pi. And many of you are like, cool, I remember how to do this. I'm not sure what that has to do with anything, but at least I remember that. We're good. Now, there are other values that are actually easy to plot on this graph of one period of cosine. Certain trig angles produce easily used y values. For example, I can get the y value of a half, like the sine of an angle or the cosine of an angle equals a half. Cosine of what angle equals a half? This is more of a question that we asked you in Unit 8. Solve this equation, cos x equals a half. Tell your neighbors, when do the cosines equal any of the halves, positive or negative a half? So, what about sine? When does sine equal a half? The cosines equal a half at the pi over 3. The sines equal a half at the pi over 6s. I'm going to actually use that fact to help me graph for the following reasons. I'm going to include pi over 3 for this cosine graph. Because I know when I plug in pi over 3 into the cosine graph, I will get a half times 2 is 1 plus 3 is 4. Oh, it will adjust my amplitude and take half of my amplitude. It'll go to 4. Two pi over 3. The cosine of 2 pi over 3 is negative a half. Oh, that'll adjust my amplitude by making it a negative 1, which means I'm going to go down 1. And all of a sudden, I have some points in between my maximums and my midline. Is that cool, Luke Rowe? Great. So we also have 4 pi over 3. We also have 5 pi over 3. Why are we using the pi over 3? Because those are the angles where cosine equals a half. If this was a sine graph, I would use pi over 6s, because pi over 6s makes sine a half. Cool. And now, what I've actually just created is a table of coordinates. Now you're like, great, these are x, y coordinates. Yeah, I understand that, Mr. Mester. This is how we graph 3 plus 2 cos theta. But look, over here, we are replacing y with r. So we could think about these values as being r's. We're replacing x with theta, so we can think of these, obviously, values as theta. Which means you have 1, 2, 3, 4, 5, 6, 7, 8, 9 points that were very easily produced, which now can be graphed on our polar coordinate system. Now, the polar coordinate system is nothing special. It doesn't I can't stand when this happens. It doesn't change anything. It just helps you plot certain points. There we go. When you go Desmos, and guys, this is helpful for your SAT potentially, you go to this, you can click on this button right there. And all it is polar instead of you didn't use Desmos on the SAT? Oh yeah, that's cool. So notice, polar mode versus rectangular mode. Nothing changes. The graph doesn't change. It's just it's easier to see certain points that are plotted in the polar system. So let's go back. And I would like you to plot the polar coordinates, radius 5 at an angle of 0. Plot that. Angle 0, radius 5. Then, angle pi over 3, radius 4. Plot plot that. Then angle pi over 2, radius 3, plot that. And keep going and see if you can see what this graph is going to look like. Which one is it? Nice, Nat Dove. Keep going. You can do it. Nice.
I'm helping. I did help him. Tell him, Marcus.
For real?
Yeah.
Go get your homework, bud. Like, we're actually doing our homework right now.
But I'm gonna do it. I'm gonna struggle through it. We struggle really hard.
You sure you're okay, Barry? Yeah, you're just tired? All right, good, Barry. You gotta take care of yourself, bud. You taking care of yourself? Yeah? I hope so, Barry. Sometimes I worry about you. Yeah, careful. Okay, now, one extra thing before we connect the dots that we need to be careful of that is important. If I connect these 2 points with a straight line, I am wrong. I know for a fact I'm wrong because of this reason. Between the angle of 0 and pi over 3, my radius is between 5 and 4. Let's think about the radius of 4 and the radius of 5. It's right here. That means when I connect these 2 points, I need to be between the radius of 4 and 5. If you connect with a straight line, you are crossing through that radius of 4, and you are saying, oh, at the angle pi over 6, I have a radius that's less than 4. That's not correct. At the angle between 0 and pi over 3, my radius is between 5 and 4. So I need to stay in this like channel here when I connect these 2 points. So we're going to be careful. We are going to make sure we're kind of curving. And what else do you notice? The graph of y equals 3 plus 2 cos x is decreasing. How does that translate to the polar graph? Not necessarily that like it's going down. No, it's not going down. But how does this graph going down respond to this graph? Tell your neighbors. The radius is decreasing. The radius is decreasing. So I should be getting closer to the radius of 4 as I get closer to the angle pi over 3. If this decreases, my radius is decreasing. I'm getting closer to the origin. You see, under boom, says how is the distance between the origin and f of theta comma theta changing on an interval from pi to 3 pi over 2? From pi to 3 pi over 2, this graph is increasing. What does that mean? My radius is increasing. I'm getting further away from the origin. So be careful as you connect your points. Stay in the proper channel. The closer you get to pi over 2, the closer you get to your radius of 3. Closer you get to your radius of 2. The closer you're going to get to your radius of 1, back up to the radius of 2, back up to the radius of 3, 4. I made a mistake. I crossed through. I cannot cross through. I have to stay in my channel of a radius between 3 and 4, and then I have to stay between 4 and 5. And we create this heart shape. Okay, you guys do the next one, 3 plus 3 sine x, all by yourself. Beautiful. Now, guys, we have the graph of sine. Remember, sine at the pi over 6's gives us the half of the amplitude, puts us in between our midline and our max. The pi over 6's are the angles that I care about for sine. The sine of pi over 6 is a half. So as we plot important x values, throw in the pi over 6's, not the pi over 3's, because for the sine graph, the sine of pi over 3 is root 3 over 2. Okay, you got it? Okay, let's see. All of the pi over 6 is between 0 and 2 pi would be great. All of the pi over 6. Yeah. I do think it's funny. Your reaction to like a little bit of extra work is funny, Val. All of the pi over 6's? Yes, Val. I think that's funny. What did I make a mistake with? No. That's funny. Okay. The sine of pi over 6 is a half. I'm taking this 3 and I'll multiply by a half, which makes it 1.5, which puts me in between 3 and 6. The sine of 5 pi over 6 is a half times 3, puts me halfway in between the midline and the max. We'll get 1.5 and this is a quick table of values created. Stay in the channel. You're not staying in the channel. Stay in the channel. I mean, it's not actually that bad. Wait, no, you're pi over 6. This is your error. At pi over 6, you have 4.5. You got 4.5. Okay, cool. You got to go from the angle 0 to the angle pi over 6. You should be connecting here from 0 to 4.5 there. You can't go past. You can't go below the angle of 0. Well, what I'm noticing is that if you're doing it by yourself, you're connecting the dots wrong, okay? And that's okay. We need to practice. Maybe instead of doing all the points, just do one at a time and connect them 2 at a time. So, 0, 3, 0, 1, 2, 3. Your first point should be over here. Theta of 0, radius of 3. That's one point you missed. You had 0, 0. Cool? Pi over 6, 4.5. Connect these 2 points where your radius is increasing. Pi over 2, 6. Yeah, we're off the graph with you, LBI. Connect these 2 points so that your radius is increasing. You get further, further towards the radius of 6. Why do you have, so, okay, I got you. All right. Next, 5 pi over 6, 4.5. 5 pi over 6, 4.5. I need to decrease my radius so I get there. Pi, 3. Pi, 3. Cool. 7 pi over 6, 1.5. 3 pi over 2, 0. 11 pi over 6, 1.5. 2 pi, 3. That butt shape again. Okay? Now, one more before we go. What is happening between pi and 3 pi over 2? My radius is decreasing. My y's are decreasing. We are getting closer to the origin. Now, last thing. Seven A. We got a horizontal dilation, people. It's going to affect my period. But we are only asked to graph this from 0 to pi over 4, which means, this is pi over 4, which means I don't care about what happens after here. I just care about this amount. We will get more into next class what happens when radii go negative. But all you have are 2 points, 0, 4, and then pi over 4, 0. But make sure when you connect them that you don't go over the angle pi over 4, or else you're breaking the graph. When you get to the angle of pi over 4, you get 0. You should be thinking about angles in between 0 and pi over 4. Do your homework. Hey, I did the homework video. Good job not answering that.